Welcome to a lesson on section 3.5, derivatives of trigonometric functions. So the goal is to find some shortcuts, some things we can memorize to make this a little bit fast. So we're going to begin by examining the derivative of the sine function. And so to do that, we'll use our limit definition of a derivative function from section 3.2. And so if you use that, all you're really doing is plugging x plus h and x into the function sine x. So it probably follows that first line that you have sine of x plus h minus sine of x over h. And what you need really is an identity that you may or may not have memorized from your trig class, from your pre-calc class, and that is the addition formula for the sine function. Sine of a plus b is equal to sine a cosine b plus cosine a sine b. And that won't be on the test, so don't freak out about that, but that's an identity from your trig function, from your trig class. And so I just inserted that in where my a and my b are x and h, and you can see that expanded out to all of that. Then I did a little bit of rearranging. I moved this last term here, I moved it forward one. You can see that I did that, and split it into two fractions here and here. And the first fraction, you can factor out a sine x from the numerator. They have a sine x in common, and you get this first term here. The second one, I really wanted to hyper focus your attention on the sine h over h. And so now we have two trig limits from chapter 2. One of them is the cosine, in this case x, h rather than x, but cosine h minus 1 over h as h goes to 0. This right here will be a 0, so that goes here at the bottom, so it's sine x times 0. Of course, that will just be 0. And then on the right hand side, remember that sine h over h as h goes to 0 is 1, so that's tracking here. So we have cosine of x times 1 is just cosine x, and so of course 0 plus cosine x is cosine x. So there's a lot to that proof there. You can re-examine that, but what we learned in the end is that if we take the derivative of the sine function, here's our shortcut, the answer is cosine x. That's nice. Now you can use a similar approach for the other trigonometric functions: cosine, tangent, secant, cosecant, cotangent. And you can get the derivative of each doing something similar to what we're doing here. Of course, they all play out a little bit differently as the identities will change a little bit for each one, but we'll leave some of that for class. Okay, but here they are for now. Here are the 6 things to memorize. The derivative of the sine function we just did is cosine. The derivative of the cosine function will be negative sine, and that's because the identity has a minus sign in there, and there's a reason for that, but those are pretty easy to memorize. The derivative of the tangent function is secant squared x. Remember that means secant x times secant x. Maybe I'll write that down here just so you recall that from your trig course. If you see that, what that really means is secant x squared, like that, or in other words, secant x times secant x. That's what that notation means. Moving on. The derivative of the cosecant function is negative cosecant x cotangent x. Derivative of the secant function, secant x tangent x. And the derivative of the cotangent function is negative cosecant squared x. These will take you a few moments to memorize. What I suggest is looking at the list, repeating it off, and then writing it repeatedly until you have it down and you can write it from memory. Generally, you can put it in about 10 minutes now, you can put it in about 10 minutes tomorrow, 10 minutes the next day, and then you pretty much have it. It usually only takes about that amount of time to memorize these. It doesn't take too long. So let's find a derivative of a function here, and let's look at our first example down below. So we have the derivative of fx is 5x cubed times sine x, and it's invisible, but there's a little multiplication symbol. So we're going to be using the product rule. Use the product rule. So let's write that rule down. You might recall that if you take the derivative of two functions multiplied together, I'm just going to abbreviate it fg. It'll be equal to the derivative of the first function, f prime times g plus f times g prime. So we're going to tap into that formula right now and identify here in our function that our first function is 5x cubed, our second one is sine x. So using the product rule and now our new trig definition. So the derivative of the first using the power rule should be 15x squared. That's our f prime times the second function, sine x, plus the first function as is, 5x cubed, times the derivative of the second function, that's g prime, and the derivative of sine we learned earlier is cosine. And sometimes you would do more if you can combine like terms. If you were going to solve or something of that nature, you might factor. But in this case, I'm just going to leave it as is and feel pretty satisfied with that. That's my derivative function. Let's try number 2. Gx is sine x cosine x. Again, there's an invisible multiplication symbol, so I'm going to use, again, the product rule from above. So g prime of x, first the derivative of the first function, the derivative of sine is cosine, times the second function, just leaving it the same, cosine, plus the first function as is, sine x, times the derivative of the second function. Now the derivative of cosine, I didn't prove that, but it's up here in the list, is negative sine x. We're going to multiply that by negative sine x. So that can be written better as, this is where simplification is necessary, cosine x times cosine x, cosine squared x, sine x times negative sine x is negative sine squared x. Alright, so that's a better simplified answer. Let's take a look at number 3. And number 4, we're going to have some use of the quotient rule. So let's recall what that is from an earlier section. A quotient rule, and I will just abbreviate it here. If you have the derivative of a function divided by a function, say f over g, it's f prime g minus f g prime over just g squared. So let's take a look. H prime of x then will be equal to, in the numerator, first derivative of the top. Now you can look at your printout here, but the derivative of the tangent of x would be secant squared x times g, that's just the bottom function as is, that's 4x squared, minus the top function as is, tan x, times the derivative of the bottom function, we'll use the power rule, that's 8x, all over the the denominator squared. Again, you'll clean this up as is. Generally, it's pretty accepted to write the polynomial piece in front of the trigonometric function, so it's probably better written as 4x squared secant squared x, and then minus 8x tan x, all over. And again, if you wanted to square this, you could square 4x squared squared. 4 squared is 16. X squared squared is a power rule. Power to power rule, x to the 4th. And that's a pretty good answer for your derivative function. You see, it's got a lot to it. Last one, number 4. Again, we'll use the quotient rule as we just did. So the derivative of the I function, derivative of the top, the derivative of x is just 1 times the denominator, secant x, minus the top function x times the derivative of the denominator. The derivative of secant x, you can again look from the chart above, is secant x tangent x, all divided by the denominator squared. Oops, forgot my x. There we go. Again, you can clean it up if necessary. Write it 1 times secant x is secant x, and then on the right hand side you just have x, secant x, tangent of x, and probably on the bottom it's best written as secant squared x. And you could do more with factoring if you want. You know what, let's do that here just so you can see it. It's probably important to see it. You might notice that the numerator both have a secant in common, so you could factor that out. This is going to be nice, 1 minus x tan x. And on the bottom, remember that secant squared x, that's just secant x times secant x. And then you can see that these will in fact simplify once you have it factored. So yeah, this is a better answer. Let's use this one. 1 minus x tan x over secant x. This is the simplified answer. Of course, these are equivalent. The one on the bottom is simplified, so it's better. Okay. So you might pause the video and try these two and look at the chart above and memorize it. Okay, if you tried that, great. Let's just see if you got it right. So the first one, the derivative of the j function. If you look up the cosecant x, you should have got negative cosecant x cotangent x. And then on the second piece, this term, you have to use the product rule. There's a little invisible multiplication there. So we're going to use the product rule for that. So the derivative of the first, the derivative of x is 1 times the second, tan x, plus, this is all, I can put parentheses even though you don't have to, just you can see I'm using the product rule, plus the first function, x, times the derivative of the second. So the derivative of tangent is secant squared x. Alright, so there you go. And again, you might be able to clean that up. You might be able to factor something out. It doesn't look like there's much to clean up here. That first term, negative cosecant x, cotangent x. And then we're just adding 1 times tan x is tan x. And then x secant squared x. There's not really much to do here to clean this one up, unless you can find some identity that I'm not seeing off the top of my head. So I'll just leave it like that. Number 6, if you tried this one already, k prime of x. The derivative of the tangent function is secant squared x. And remember, 2 is just a constant multiplier. And then the derivative of the cotangent function is negative cosecant squared x. But we have a minus sign already there, so if minus a negative, I'll change that to plus cosecant squared x. Again, this doesn't clean up much, so we'll leave it there. Now let's go ahead and look at some problem where we apply our value, our derivative function. So this one says, find the equation of the line tangent to the graph of mx equals sine x minus cotangent x at x equals pi over 2. Remember, what we need for the equation of the line is a slope and a point. Right? We're going to use this y minus y1 equals m times x minus x1 approach. So let's go ahead and get the point first. So our point at x is pi over 2. We're just going to find the value of the point by plugging pi over 2 into the function. M of pi over 2 will be sine of pi over 2 minus cotangent of pi over 2. Alright, so you got to know your unit circle for this. And let's make a little sketch of this for you here. You might remember your unit circle. Quick drawing right there. And pi over 2 would be up here at the top, right? Pi over 2 radians would take us to that location right there. So the value of that point right there is over 0 and up 1. So if you remember your definition for sine, the sine is just the y value. So sine of pi over 2 is going to be 1. You might remember cotangent. And I can write this over here if you've forgotten your cotangent formula will be x over y. Remember, tangent is y over x. Cotangent is just the reciprocal, x over y. So our x value here is 0, and our y value is 1. And so this is 1 minus 0, or 1. So that will be our point. Let me write it down. When x is pi over 2, y is 1. That's what we learned, right? When we plugged in pi over 2, we got out a value of 1. Now, so we have x1 and y1. Good there. Now we've got to get at the slope. That's the other thing we need, and that's where the derivative comes into play. So let's find the derivative function. The derivative of sine is cosine, and the derivative of cotangent is negative cosecant squared x. But we have minus and negative, so that'll act like a plus. Cosine x plus cosecant squared x will be our derivative function. Now, we want the derivative value, the slope, when x is pi over 2. So now we're going to plug that in. M prime of pi over 2 will be cosine of pi over 2 plus, I'm going to write it like this, cosecant of pi over 2, whatever that value is, squared. Alright, so cosine of pi over 2, we already made our drawing. Remember, the cosine is going to be the x value. So that's 0. And then the cosecant is going to be the reciprocal of your sine value. Now, we already know the sine of pi over 2, we found in the previous one, is 1. The reciprocal of 1 is still 1. And 1 squared is 1 plus 0. Final answer, 1. That's going to be our slope. All right, so our m is 1 for our line. And now we have all the parts we need. All right, so y minus y1, right over here, equals m, that's the derivative, times x minus x1. That's the pi over 2. All right, I like to put all of my lines in y equals mx plus b form, so let's go ahead and do that. If we distribute the 1, we're just going to get x minus pi over 2. Add 1 to both sides. We get x minus pi over 2 plus 1. Now, that doesn't look exactly like y equals mx plus b form. If you put parentheses around this, then it looks more like it, right? So your slope is 1, and your y-intercept is at the point negative pi over 2 plus 1, which is just a number. Crazy number, but a number. So there we go. We have our equation of our tangent line. All right, let's do number 8. Given that y is x sine x minus cosine x, find the second derivative of that function. Okay, so that just means we have to do the derivative back to back. Let's go ahead and find the derivative first. All right, we've got to use the product rule in the first one. Derivative of x is 1 times the second function plus the first function x times the derivative of the second function cosine x. So that was just for this part of the function. I used the product rule. The second one's a little more straightforward. The derivative of cosine x is negative sine x. Before I do the second derivative, I always like to clean this up as much as I can. So I have 1 times sine x, that's just sine x, plus x cosine x, and then minus a minus plus sine x. And notice we have like terms, 2 sine x plus x cosine x. That's about as clean as I can make that. So let's go ahead and move on to the second derivative. So d squared y over dx squared. What we're going to do is take the derivative of this, right? We're going to be looking at that to evaluate our derivative. So let's figure out the first term, 2 sine x. 2 is just a constant multiplier, and the derivative of sine is cosine. So that's the first part. The second term, again, the product rule. Derivative of the first, 1 times the second, plus the first x times the derivative of the second. The derivative of cosine, negative sine. Again, clean this up the best you can. Let's see, 2 cosine x. 1 times cosine x is just another cosine x. Here we have a negative, so we have x sine x with a minus sign. These are like terms, so 2 cosine x plus another cosine x would be 3 cosine x minus x sine x. That would be my second derivative. So kind of cool. Can do it back to back. The trick, not really a trick. The strategy really, though, is make sure that you have that first derivative simplified as much as you can before you plug into this, get plugging on the second derivative. It just makes it a lot easier. All right, number 9. Here we go. This is our last problem, a little application problem. Imagine a particle moves along a coordinate axis in such a way that its position at time t is given by this function s of t, and I apologize that it goes under the next line. I don't like when it does that. S of t equals 2 sine t minus t on the interval from 0 to 2 pi. Now, this is a funny little story, of course. Imagine, you have an axis here, right? Right? This is just the t-axis. And from the time 0 to time 2 pi, our particle is just moving around on the axis. So one way to think about it is like, well, what's going on with it? And you can just think about like, at the beginning, it's at s of 0. 0 is where we start. If you just plug 0 into the function, you get 2 sine 0 minus 0. Sine of 0 is 0, minus 0 is 0. So like when you start this problem out, the particle is sitting right here. But the particle is going to move around. It says it moves along this axis. So sometime later it's somewhere else, sometime later it's after that. This is a position function right here, s of t. It just tells you where it is at any time. Like for example, I wonder where it is when we're at time pi. And you just plug in and see where it's at time pi. And so sine of pi would be 0, 2 times 0 minus pi. Now it's located at negative pi, so somewhere back over here. So the particle is back over here. But the reality is we don't, I'm not doing every point, so maybe the particle's kind of jumping back and forth along this line. That's really messy how I drew that. But anyway, that's what's going on. It's just a position. Let's go ahead and do what the problem asks, though, because this one says, at what time is the particle at rest? The key phrase is this particle at rest. When something's at rest, it's not moving, right? Not moving. And another way to think about that is something's not moving when the velocity is 0. Like if something's velocity or speed is 0, then it's just not moving at all. Well, if we have a position function, s of t, you can recall from previously that if we take the derivative of s of t, s prime of t, we're going to get that velocity function. So that's our first step to solving this. This over here was just exploratory. You don't have to do that, all right? But we're going to, the real meat of this problem is on the right here. So let's first figure out what is s prime of t. So the derivative of 2 sine t would be 2 cosine t. The derivative of sine is cosine, minus the derivative of t, that's just minus 1. And we want to know when is this, by the way, this is our velocity function. Right, that is our velocity function. We want to know when is the velocity 0. When is this function equal to 0? That's an equation we can do, figure out. We're going to solve where 2 cosine of t minus 1 is equal to 0. At 0, right, at rest. All right, let's add 1 to both sides. Divide by 2. And then t will be the inverse cosine of 1/2. So I want you to think about the unit circle of like, where would the cosine value be 1/2. Okay, so knowing that unit circle is very helpful, but just as a reminder, you're kind of memorizing like where, in this case, the interval from 0 to 2 pi, which is all the way around the circle, right? Where's the particle at rest? So you might recall that this position here, right, that's at pi over 3, the pi over 3 position. That's a really ugly picture, but anyway, that point would be 1/2 comma root 3 over 2. And that's where our cosine would be 1/2. So then you can just use logic to think about where else would the x value be 1/2, and that would be mapped down here at this position where you have this 1/2 comma negative root 3 over 2. And so then really that's just, this one might come to mind right off the bat, but then you just have to think like what would that one be? And you can use a little bit of logic to think about it. If it's 2 pi all the way around and you're coming back pi over 3, then you're just thinking about like 2 pi, take away 1/3 pi. So you have that 5 pi over 3 location at that spot. So those are your two locations where the velocity would be 0. I'll write that as a solution set. T is both pi over 3 and 5 pi over 3. There's two solutions because this problem asks us within that interval. So I'm using a lot of trig remembering on this particular problem. That's all for this video. See you next time.